Good. So, evaluating ANN efficiency in recognizing electroencephalogram and eye tracking, evoking potential in visual game events. I'm Andreas Wolf Jensen. I've done this study together with Luis Emilio Broni. Alright, so here's the content of today's presentation. First of all, I'll go through the idea and inspiration for this study. Then I'll visit the experiment procedure and setup. Then I'll go through data processing, the artificial neural network, the results, conclusion, and a little discussion in the very end of the whole study. Good, so let's get started. So, idea and inspiration. First we were wondering, when we have psychophysiological measurements, as for instance electroencephalogram, we tend to have an idea of what we're receiving, seeing all these nice curves, like for instance the P300. And with that comes also a very simple stimuli, like for instance the spelling machine, where you set that certain characters should be highlighted at a certain point, and when that happens, the P300 is elicited, and you know that. So there's a certain relationship between the simple stimuli and the electroencephalogram you recorded. Super nice. But what about more complex stimuli, like for instance games? Here we have a multitude of different things happening at the same time, a lot of audio, a lot of visual stuff. And in that sense, we'll also have the psychophysiological measurements being a multitude of different things. And can we make any visual sense of this? Well, the chances are possibly not. So, how will we then do about this? How will we go about this? Seeing a relationship between the psychophysiological measurements and the game itself. And what is really good at patterns, so we can see if there is any. Deep machine learning. Good. So we chose to go with the artificial neural network, which is essentially a super smart algorithm. It has been trained previously to find different things as cats in a dataset of 100,000 images and with a very high accuracy. So that's super interesting, and we know images are a multitude of different things happening at the same time with a lot of variables. So why not see, can it efficiently see the relationship between the psychophysiological measurements and the game? Maybe. But one thing is for certain, is that it has been proven previously that with simple stimuli and known psychophysiological measurements, how that looks, the ANN had trained to have a very high accuracy, around 90% and higher. So this should be a possible venue that should do the same with complex stimuli and its psychophysiological measurements. So for our experiment, here comes the procedure and setup. So first the game itself. We chose to go with Super Mario, as it has a little palette of different game events and different things that can happen, and we have the total control of designing wherever this should be doing. Of course, at a certain cost, because we don't know how the player will play the game, but we know for certainty how the design of all levels were. So we decided to design 10 homogeneous looking levels. First of all, having a jumping area in the very beginning, and then having an area with a lot of enemies and boxes in which the user can interact with. Good. And some of these events that could happen are, for instance, these four, being Mario jumping up in a box and something happens. So, with these events in mind, are there any certain patterns which are unique to each one of them? We'll soon figure out. So, we decided to set up a 16 electrode electroencephalogram array, widely spread around the scalp, and we use the eye tracker to record pupil, gaze, direction, and position, and we have pupillometry as well. Good. So we tested out. 31 test participants were playing this game together with their electroencephalogram and eye tracking being recorded. Good. And then this experiment took around 10-15 minutes per participant. Nice. So now for the data processing. So the first thing we did was to go through something called triggering, being dividing all the data into with respect to all the events that happens. So in that sense, having such thing as epochs. In this case, it was 1 second before the event onset and 2 seconds after the event onset, as many eye track data could have significance within this range. Good. And then we now looked at all the epochs and extracted all the noise and muscle activations. And we went through independent component analysis to get rid of the last piece of noise. But all this filtering come at a certain expense, seeing that we need to take out quite a lot of epochs, and thus quite a lot of events. So we reduced the amount of useful subjects from 31 to 13 just, and the useful amount of events from 33 to just 4. Because we had this prerequisite in order to have a nice classifier, a nice model to see the relationship, it needs a certain amount of data. And for our sake, we've decided that this certain amount of data should be at least 20 events, epochs, per test participant. So here we have it. 80 epochs or events per participant in total, be like 4 times 20. And in total we have 1,040 events which were classified. Good. So the events in mind which we have used in the study were these 4. The first 2 being Mario jumping up in a box and something happens, which will be jumping out into an empty box, the box explodes, and again the other one where the box contains a single coin. The 2 other events being Mario killing an enemy either by stomp or by a fireball. Super nice. So, of course, as with any machine learning, we need to model our data. We chose the following distribution, being 70% to the training and 30% for testing. And we ran all through 10-fold cross-validation to avoid overfitting. And this very discussion about overfitting, we'll come back to that just later. Good. And now for the network itself. We chose to work with the NCOG framework, which is a nice little framework developed for instance, C# in which we coded in. And with neural networks, there's one thing that always is a good question. How should the structure be? As nobody knows from the very get-go how many hidden layers and how many input layers, how many layers and how many neurons that should be. Good. So for the input layer, super simple, because for the electroencephalogram we need 1 second after the onset, being 256 neurons, and for the eye-tracking we need the whole epoch being 1 second before, 2 seconds after, 768 neurons for the input. Super. So that was super easy. What about the other layers then? The other hidden layers. Well, that's a bit tricky. So went down, tested 4,500 models, ranging from 1 hidden layer with 1 neuron to 3 hidden layers with 20 hidden neurons in each. Good. And then we took the 3 most efficient networks, those with the highest accuracies. This test was based on the electroencephalogram data. Good. Then we took the 3 most efficient one, trained them with different amount of iterations up until 10,000 and figured the final best neuron network being with 3 hidden layers, 16 neurons in the first hidden, 10 neurons in the second, 9 neurons in the last one, and it was best at 7,700 iterations. Super nice. The same process went on with the eye-tracking as well, reaching this network being the best. 2 hidden layers, 16 neurons in the first hidden, 12 neurons in the second hidden, and best at 2,400 iterations. Great. Now we have our data. We trained through the network. So how well did it perform? First here we got the results. And the results are all the things are the same now are averages. First, these averages are based on the network training 10 times the same data. It listed 10 different accuracies. I've averaged those guys. Taking this one, we have 13 participants, so we have 13 of these. The average of those. Good. And that will be the very numbers I'll be presenting. And now for the different events and how well they were classified. Starting up with Mario hitting an empty box. Good. We have now for the electroencephalogram trained network, we have accuracies ranging in the 60s, in the mid 60s from 63 to 66. And we have for the eye-tracking trained network, we had accuracies from 55 to 60. A little difference there. And now for the precision. Precision is quite interesting here. I'll of course come back to that discussion later. Because here we have higher precisions for the eye-tracking, but lower for the electroencephalogram trained models. Good. And now, for Mario hitting a box containing a coin, we have the same thing here going on, we have for the electrospheric trained network, simply having the accuracies in the mid-60s, and for the eye-tracking trained network, we have the accuracies in the late 50s. And with the precision in the mid-70s, both of them, it seems to kind of equally performing with respect to that event. For the next one, Mario killing an enemy with a stomp, we have our accuracies in the 60s as well, for both of them. For both the EEG trained and for eye-tracking trained models. The eye-tracking trained model was also in the 50s as with the other guys. We had the precision also in the mid-20s for both of them, while the highest one being recorded for the highest average for the electrospheric trained network. Good. Now for the last event, which is also a rather super interesting event, because we have here accuracies in the 70s instead of 60s for both trained models, and we have our precisions way lower, down around 10 on the average. Now that's quite interesting, and I'll of course come back to that in the discussion. So now we have our results, and a simple conclusion can be set that theory is a promising venue of using artificial neural network to train the psychophysiological measurement with respect to complex stimuli, and thus seeing the patterns which we cannot see. Because we have these accuracies ranging from 60 to 72, and we have our precisions ranging from 22 to 27 at the highest average recordings. Highest average accuracies. Good. So, discussion. What can we discuss about this? Because there are definitely a lot of things which could have influenced these results. First of all, we can look at our network, which can be very well prone to overfitting, as our dataset was quite small. Only 56 events was trained on and then tested on 24. It's quite a little dataset, thus very prone to overfitting, and it has only known a very little amount. Another thing, we could have changed the network to a convolutional neural network, for instance, as Coquetti has trained this on figuring out how to classify workload, cognitive workload, ranging in the 1970, accuracies in 1997, being a rather good classifier indeed for that. And thus it could very well be a very good classifier for this kind of problem as well. So, and for the very events in which we use, one thing we can see something with the accuracy and precisions, because with the three first events, the accuracies were at the 60s, meaning they were quite looking like each other, as they were as high, also quite hard for a classifier to distinct them. While we have somewhat high precision, thus there was some individuality in their patterns. So with the fourth one, having high accuracies, meaning that Mario killing enemy with a fireball looks quite dissimilar to the three other events, but having lower precision as well could indicate that the very epochs which are with respect to this event are definitely dissimilar, which can be explained by the progress of the game, as what could happen is three enemies are spawning at the same time, the player is super eager to shoot at it, and shoots all of them within 1 second. Thus, all the electrospheric epochs looks quite dissimilar. Now one thing here is that we have looked at singular events, and we're very structuralistic about it, but how about if we say sequence of events, because this could indeed unlock how the user was thinking and the player was thinking while playing the game, as his progress in the game is very dependent on the context and what is happening. As it also mentioned, like every time he's doing something, he's constantly re-evaluating what he should do afterwards. So the strategy of his game is very different from beginning till the end. And thus the sequence of events, by analyzing the electrospheric or eye-tracking data with respect to that, could open up some other things. Other interesting things indeed. So, thank you very much for listening. I'm Andreas Wolf Jensen, research assistant from Aalborg University, Copenhagen, and here's my contact email. And just last, here's some references, which I used in the slides.